All right, this is my submission for homework one, where we're going to be running linear and nonlinear regressions on the Antoine equation based on experimental data to figure out the arbitrary constants A, B, and C. And without further ado, let's get started with the nonlinear regression. First thing we want to do is open X. No, I'm just kidding. I'm kidding. Let's get to the real stuff. Okay. Um, well, it looks like I didn't clear what I meant to clear, but as you can see, the very first thing that you want to do is get the .csv file from GitHub. And what that involves is a shell command called wget, and then the link. Remember, you want the raw link from GitHub. So this is what you immediately see when you pull up the CSV file. You want to hit raw and get that URL right there and run it. Well, evaluate it. And it evaluates correctly, all that nice stuff. And we can get started with evaluating the rest of the code. So, first thing we want to do is to import your necessary packages. The first of which being numpy, so import numpy as np. And we also want to use a package from SciPy called optimize minimize. So from scipy.optimize, typo, import minimize. Okay. And finally, we want to be able to plot things, and we're going to use Plotly for that. So from plotly.subplots import make underscore subplots. Okay, and we're wanting subplots because we want to be able to put more than one data set on a single plot. Oh, that's the explanation anyway. And just because we want it to be in dark mode, let's go ahead and import plotly.io as po and run the command po dot templates. I think that's the correct one. po.templates dot default equals plotly underscore dark, and everything evaluated correctly, so we're smooth sailing for now. Okay, with importing the packages out of the way, first thing we want to do is take that CSV file and put it into a numpy array. Quick reminder on what a CSV file is. It's essentially a text file of comma separated values. That's what the CSV stands for. So we want to use a numpy command. Well, first we want to call the object data. Okay, and we're going to use np.read. Oh no, not read. Load? Yes, load txt. And the first argument that load txt takes in is the file name, which is water vapor pressure.csv. And you can just copy that, paste it, boom. The second argument we want to use is define a delimiter. Okay, and a quick reminder on what a delimiter is. It's any character that will be able to split up that long string in the file into individual elements in an array. With this case is a comma, because comma separated values. Let's evaluate it. It runs correctly. Fantastic. Next thing we want to do is to, actually before we do that, let's make sure that we are seeing what we want to see, which is this. Excuse me. The left column is temperature in Celsius, and the right column is pressure in pascals. And we want to put those into two different arrays, T and P. Okay? So, get rid of that. T, we want to equal to data, right? All values in row 0. Remember that in Python, arrays index starting from 0, not like MATLAB. And P, pressure, is equal to data in the second column. I apologize. Column, not row. And let's double check that. T, it's there, what we want to see. And P is also what we want to see. Okay. I'm going to, okay. The next thing we want to do is plot our data to see what it looks like. And a quick reminder on what our equation looks like. It's the Antoine equation is log base 10 of P is equal to A minus B over C plus T, right? Now, what we really want is to see what the value on the left side hand of the equation is. So let's define that into an array where log 10p, actually let's make that lowercase, log 10p is equal to np dot log base 10 of p. And you'll see why we want this value instead of p later on. And that's what we're going to plot on our y-axis. So let's make a figure object. Fig equals make underscore subplots. Is that the correct syntax? Yes, it's correct syntax. And then fig dot add underscore scatter x equals t, y equals log 10p. Mode markers, because we want a scatter plot. And name, we'll name this data. Ooh, doesn't like the syntax. What does it not like? Markers. I'm missing an S. Mode equals markers. And look at that. It's a logarithmically growing function. Okay. Now we know that our data is there, and it's set up the way that we want to. Let's move on to doing the nonlinear regression. And what the nonlinear regression really does is it's going to take a look at each of these data values and calculate how far away is each data value from the ideal line of best fit. And we're also going to use the SciPy function to minimize that error. What that error is formally called is the sum of square sum error. So define the function. We need a sum squared error function that takes in a vector of unknowns, where those three unknowns are our three arbitrary constants, a, b, and c, and unpack that from the vector that's taking in. And what we want to return is, we're going to build this equation together, all right? We want to return the square of the difference between the experimental, which is our log 10p, and our model, which is this equation. So let's start with just that equation. Okay, so our log 10p minus our model, a minus b over c plus, let's add a parentheses there, plus t. Okay. And what this is essentially doing is checking the height. What's the difference between each data point and the ideal line of best fit? Okay? But we're getting negative and positive values. And we don't want that, because we want to eventually sum all of that together and have an absolute value. We don't care if it's negative or positive. We just care how far away it is from the line of best fit. The way we get rid of that, square the whole thing. Okay? Oh, I forget. Python does not like carets. In order to do exponents, that's 2 asterisks. Okay? Remember that. And np.sum to sum all of that into one big value. It's okay. All right. We have our error function. Next, we want to use the minimize function from SciPy in order to minimize the error function and get it as small as possible in order to find what our arbitrary constants a, b, and c are. So it starts with minimize, and the first argument that it takes in is going to be your error function. A function, it takes in any function, but for our purposes, we're putting in our error function. The second argument is going to be a vector of the guesses of what our 3 arbitrary constants are. Now, ideally, you want to get that as close as possible to the true constants, or the true minimum, right? Well, we don't know that, but we can make an educated guess. We know that it's the constants for the Antoine equation of water vapor. and we know that the A is going to be around the magnitude of 1 or 2 digits, so we'll choose 1. We can play around with the values later, but maybe it works on the first try, we'll see. The second value, B, we know is something on the order of magnitude of 4 digits, so arbitrarily, let's put down 10. And again, C will be around the magnitude of 1 or 2 digits, we'll put in 0. And let's run it, and it doesn't overflow, which is good, and it says success is true, which is also good. And finally, the array that it spits out is our 3 constants, A, B, and C, right? And we look at it, and it's what we want to see. It's what we would expect from the Antoine equation for water. But to really make sure, let's plot this against our line of best fit. Or, sorry, let's plot this against our data. So, let's unpack this vector, A, B, and C. Alright, now, this function, what it's really spitting out is this whole string here. We don't want that. We just want x, the array of 10, 17, 56, and negative 36. So the way we do that and tell Python that we only want x is add a dot x at the very end. And there, it evaluates, it's happy, and we're good. Now, let's bring this plot down past the our nonlinear regression code. And the way you do that is, I think it's Control M, Control K. Oh, that goes up. Control M, Control J, Control M, Control J. Look at that. It's at the, one more. Control M, Control J. There we go. It's at the bottom. Well, let's add our plot against this. And the first thing you want to do is, we want a array going from around 300 to, 650. And we want linearly spaced coordinates, because right now, if we use our t to plot it, we have big straight lines, and it's not going to look great. Regardless, let's call this t plot, otherwise temperature for the purposes of plotting, equals np dot linspace. Now remember, linspace is the numpy function that creates linearly spaced array from start to stop, and we can tell it how many we want in between. And like I mentioned, we want 300 to 650, and let's say something like 150 points in between. Doesn't really matter, okay? Let's add our model, which is fig add scatter. X is equal to our t plot, temperature for plotting purposes. Y is equal to our equation, and I wrote it before, so why don't we just copy that, bring it down, paste. Majesty of computers, right? And remember, t is not t. T is t plot. T temperature for plotting purposes. And our mode we want to be line. And name we'll call it non-linear. We don't need underscore. Non-linear Antoine. And I think that's good. Let's evaluate it. And look at that. Good fitting line for our nonlinear regression. I'll be right back, and we will meet on my iPad to then explain how to do a linear regression. All right? Okay. Okay, welcome back. Now, to get started with our linear regression, the first thing we want to do is to get our equation in a linear form. Okay, let's write down our Antoine equation, where log base 10 of p is equal to a plus, minus b over c plus t, where p is pressure in pascals and t is temperature in Celsius. So we want to be able to get all of our constants on one side and get the left side of the equation to be a linear form. So first thing we want to do is to multiply both sides by c plus t to get rid of that ugly fraction, right? So Oh, and one more thing I'm doing is I'm going to be switching the sides of the equation just so we'll reach that linear form where the left is linear and right is our constants earlier. So on the left side is going to be a c plus t minus b. The right side is c plus t log base 10 of p. And let's distribute everything. AC plus AT minus B equals C log 10P plus T log 10P. Now notice how this term right here only contains T and P. That's the term we want on our right side, because that's what A and T ends up A, B, and C ends up defining. So everything with an A, B, or C, we're gonna want to shove over to our left side of the equation. So let's go ahead and do that. A, T, minus, because I minus C log base 10 P of P by both sides, log base 10 of P, C times log base 10 of P, plus AC minus B equals T log base 10 of P. Alright, now from here we can get our design matrix, okay? Because if you look here, this portion here is just the constants. And over here we have constants multiplied by our T and P, which is changing after each iteration. And on the right side is also T and P, which is changing after each iteration. So what does this look like? Y. Ooh. It looks like mx plus b equals y, right? Where each constant is our m. So let's create our design matrix. And the first element in our design matrix is a t1, a t2, iterating to a tn. Second element is c log base 10 p1, c log base 10 p2, iterating to a, oh, my apologies, c log base 10 pn. And again, when I pointed out that AC minus B, it doesn't have a T or P, so it doesn't change at all between iterations. So that's going to be our ones. Okay? Now quick note. We're going to define this whole term as D. And you'll see why in a moment when we write our vector of unknowns. Okay? And our first unknown is A, because that's our coefficient. Our second unknown is C. And our third unknown is D, where D equals AC minus B. And those two vectors equal our quote-unquote y vector, which is t log base 10 p, t1, p1, iterating to t n log base 10 p n. Okay, and let's name our vectors. A vector of unknowns is V. We'll call our design matrix, normally we name it A, right? But that's going to get really confusing here because it's all A, our constants are named A, C, D, B, whatever. So let's think of a different name to name our design matrix. Let's call it lowercase m. Okay? And we'll call our output lowercase o. Doesn't matter what you name it. It's just what I thought of at the moment and what's gonna work in Python. Well, let's turn this into matrix math, because we want to be able to put this into NumPy's linear algebra.solve function in order to solve for our vector of unknowns. But in order to do that, we need our m function to be a square. And in order to do that, ignore the rotating, we want it, in order to do that, we multiply it by the transpose of itself. And remember, the transpose of any matrix is just the opposite of the dimensions. So a really tall matrix, in our case, n by 3, turns into a really long matrix, 3 by n. And when you multiply it, well, matrix multiply it together, you always get a square matrix, which in this case, a 3 by 3 matrix. All right? Let's get rid of that. With that explanation out of the way, let's move on to this. Where m, multiply both sides of the equation by m, transpose of m times v is equal to transpose of m times o. And this, I did not want the eraser. And this is the equation that we're going to be focusing on in Python when we perform our linear regression. So let's take a moment, and I'll meet you back in Python, okay? All right, time to get on with the linear regression in Python. And if you see me looking down a lot, it's because I'm referring to what we just did on screen with the iPad. Create our design matrix and then plug it into the np.linalg.cell function. So we'll call this block linear regression. And the first thing we want to do is to create our design matrix. And what that's going to look like is we're going to use the np.c_ function. And what this does is that it takes a bunch of one-dimensional arrays and puts them row by row by row. And remember, our first row in the design matrix is A, T1, AT2, ATN. So all we want is T. The second row is negative. Remember the negative because that's the form of the equation that we came to. Negative C log Pn. So all we want is negative log 10 P, which is a variable that we declared earlier. Okay, and the last one is just a row of ones. And the way we create a row of ones is we use np.ones underscore like. It can be either log 10p or t because all of them is the same size. I'm just gonna choose t, and that's our design matrix. It is not happy. Oh, that is because I use brackets instead of parentheses, where I should be using parentheses. Okay, great. We'll call this M for design matrix. Next, we'll create our output matrix, which is Tn times log 10p n. So O for output equals T times log 10p. Okie doke. And remember that the form of our equation is the transpose of m times v is equal to the transpose of m times O, output. And we're going to be plugging in this and this into our linear algebra.cell function, and it's going to spit out our vector of unknowns, which, if you recall, vector of unknowns equals A, C, and D. And remember, D is equal to AC minus B. Alright, let's get into it. np.linalg.solve. The first argument is going to be the transpose of m times m. The second argument will be the transpose of m times our output. And we'll set this equal to v, well, we'll call it v underscore unknowns, if I can spell correctly. V underscore unknowns equals np.solve. Great, no issues evaluating. And remember that the vector of unknowns is A, C, and D, but we don't have B. And the way we get to B is we use the fact that D equals AC minus B and to solve for B. But remember that in our nonlinear, we already declared what A, B, and C is. So we're going to have to unpack this as different variable names. We'll call it A2, C2, and D is equal to V underscore unknowns. Okay. And B is going to equal, well, B2 is going to equal A2 times C2 minus D. And remember, we're getting that from the fact that our D, or the last position in our vector of unknowns, is equal to AC minus B. So just solve for B. And let's evaluate that. All goes okay, and let's see how it looks like plotted against our plot. And as you can see, I already tried this once, but we're starting from scratch here. So just copy the same plotting function, call this linear Antoine, and just change all the variable names to B2, A2, B2, and C2. And there we go. We now have our linear regression Antoine and our nonlinear regression Antoine. And you'll see that they're just ever so slightly different. And that includes fitting a line to a set of coordinates in order to find our arbitrary constants A, B, and C using two methods, nonlinear and linear.